When we explored Newton's first law, we saw that an object will maintain its velocity unless it's acted on by some unbalanced force. But what we did not explore in Newton's first law is exactly what is the relationship between the unbalanced force and the velocity. And that's what we're going to look into in this video. And before I go into possible theories between how these are related, let's introduce another idea. Let's just maybe every object has associated with it some value, and I'll call that quantity m. And that's a measure of how resistant that object is to a change in velocity. So resistance to change in velocity. And if we assume that every object has associated with it some value here, then we can start to think about how these might connect. So one possibility is that for a given force, I can divide it by its resistance to a change in velocity. So if it has a high resistance to change in velocity, if I'm dividing by it, then that will give me a low velocity. If I have a low resistance to change in velocity, if I'm dividing by a low number right over here, then that will give me a higher velocity. And also, the higher the force, or the larger the magnitude of the force, the larger the magnitude of the velocity, and they'll actually go in the same direction. So that's one possibility. The other possibility is I can take my force, my unbalanced force, and maybe I can divide it by this quantity m that's associated with any given object, which is resistance to change in velocity. But that doesn't give me the velocity vector. Maybe that gives me an acceleration vector. Maybe that actually gives me the rate of change of velocity. And the rate of change of velocity is going to go in the same direction of the force. And it's going to be proportional to the magnitude of the acceleration is going to be proportional to the magnitude of the force. And maybe it'll go in the same direction. There's another possibility that I introduced this idea just to trick you. Maybe m has nothing to do with it. Maybe the acceleration or the velocity are only going to be dependent on what the velocity already was. So maybe for a given force, let me do it in that same color, maybe for a given force, I am actually dependent on what my existing velocity is, or maybe my existing speed. And so if I'm already at a high speed right over here, and I divide by a high speed, I will get a lower acceleration. I will get a lower acceleration. If I'm at a very low speed, then I will get a higher acceleration. Maybe it's the other way around. Maybe for a given force, the higher my speed, the higher my acceleration. And this looks like fancy notation, but this is just saying the magnitude of velocity, which is just my speed. So I take my force, multiply by my speed, and I'll just accelerate in that direction. And so the faster I go, the faster I'm already going, the faster I will actually accelerate. So I'll let you think about which of these do you think is actually the most consistent, or the one that is consistent with the reality around us. So let's now try to think these through. And for these first two, I'm going to imagine a scenario. Let's say I have a truck. It has a truck. And let's say a truck has a high resistance to a change in velocity, if you've ever tried to change the velocity of a truck without an engine. So I have a truck right over here. I have a truck right over here. And let's say it's traveling in this direction its velocity is 100 meters per second to the right, which is very, very, very fast, especially for this thing that has a high resistance to change in velocity. So I'll just write high m right over here, and it's obviously going in that direction. Now let's imagine that there's me, and this truck is right about to hit me, but then I press on this truck. I apply a force to the truck in the opposite direction. So I apply a force in the opposite direction, and let's say that that is a 1 Newton force. And you might not have a sense for exactly how much 1 Newton is, but let me just tell you that that is a force that I am capable of applying to a truck. So I apply this force in that direction just like that. Well, based on this theory right over here, everything will be okay. I will not be hit by the truck because I'm applying the force to the left. This formula right over here tells me that the velocity of the object that I'm applying the force to will immediately take the direction of of my force. The force and the velocity have the same direction. So somewhat magically, the truck will just turn right around. It might not go very fast in the other direction because this has a high m, but it'll immediately turn around. Well, that's not consistent with our everyday reality. We know no matter how hard that I might push on that truck, it is still unlikely to stop, much less actually change direction. So this right over here does not make a lot of sense. Let's see if this one makes sense for this scenario. Well, this one, it tells us that I'm not going to actually change the direction of the object. I'm not going to change the velocity, but I will accelerate it in the same direction as my force. So I applied a force in that direction of 1 Newton. That tells me that I'm also going to accelerate it in that direction. If I'm accelerating it in that direction right over there, so if I'm accelerating it to the left, so that's my acceleration. If I'm accelerating it to the left, that doesn't mean that all of a sudden the truck is going to start going to the left. It just means that its velocity is going to start, I guess one better way to think about it, if the velocity is already going to the right and I'm accelerating it to the left, the magnitude of the velocity in the rightward direction is going to get smaller, or it's going to decelerate, which makes sense. It might not decelerate a lot because 1 Newton is not a lot of force relative to the truck, but it might decelerate a very, very, very minuscule amount. And if I were to apply a large enough force, or the larger my force gets, the more I might be able to decelerate. And if I was the Incredible Hulk, maybe my force would be large enough to decelerate it a good bit, or maybe even bring it to a halt. So this actually does not seem that inconsistent, at least with this scenario right here. Now let's think about this one over here. Maybe the faster something is going, the less of an impact the force will have on acceleration. But this starts to break down when you think of the edge cases. This tells us that if my velocity is close to 0, so if I have a very, 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 very small velocity, a very, very small speed, actually, the magnitude of velocity is very, very, very small, then if I apply any force, I'll get a super high acceleration. I might get close to an infinite acceleration, especially as the velocity close to 0. In fact, this whole formula breaks down when the velocity is 0, when I'm actually at rest. So this actually doesn't even describe the at rest state. So this does not make sense. And this one right over here also breaks down at rest. It says if the magnitude of the velocity is 0, I'm at rest, then no matter what the force is, I will have no acceleration because anything times 0 is going to be 0. So this also does not make sense. And so this one was consistent with what we experience every day, and the other ones were pretty easy to get rid of. And this indeed is actually the case. And you might be more familiar with it if we were to multiply both sides of this formula or this equation by the quantity m. If I multiply both sides by m, right over here, then I get force is equal to my quantity m. I'm just going to swap on the left side, these just cancel out. On the right side, I get my quantity m times acceleration. I just switched the order of this. So my quantity m times the acceleration. And we get quite possibly the most famous formula in all of physics. And this is what Newton's second law tells us. Now you might say, that m all of a sudden looks very, very familiar. It probably looked familiar from the get-go. And if you're guessing that m is mass, then you are absolutely correct. Every object has a quantity associated with it, which is its mass, which is its resistance to change in velocity. And you might say, well, I thought mass was how much stuff there is. How much, I'll put stuff in quotes, how much stuff there is, or how much matter there is. In our everyday world, that really is what mass is. And we'll see that that's still a different thing than weight. But in our everyday life, how much stuff or how much matter is how we conceptualize mass. But especially as we get into kind of the subatomic and the quantum scales, how much stuff there is starts to not make that much conceptual or intuitive sense. And so a pure definition for what mass is actually is a resistance, a quantity that measures an object's resistance to change in velocity.